In this second video on equilibrium, we're going to focus on Le Chatelier's principle, and we're going to talk about how to predict the response of a system when it is at equilibrium. We will talk about how a system can be disturbed by changing the concentration of a reactant or product, changing the pressure that the system is under, or changing the temperature by adding or removing energy. Le Chatelier's principle is a law based on observations which says when a system at equilibrium is disturbed by some change, the system will respond in such a way to reduce the effect of that change and reach a new equilibrium. So, as we had said, we're going to look at how we can disturb a system at equilibrium by changing the concentration, changing the pressure, or changing the temperature. A few phrases that you might need to know are, you'll hear me saying things about the system will shift towards a certain direction, or it'll shift forwards or reverse, or the system will favor. All of these things in this way of writing it, when we're referring to the products or the forward direction, all of these phrases mean that the rate of the forward reaction will increase so that more products are made. If we were talking about a change that shifts towards favoring the reactants, we would just change our phrases to say it will shift towards the reactants, or shift in reverse, referring to the reverse direction, or the equilibrium will favor the reactants. All of these phrases mean that the rate of the reverse reaction will increase so that more reactants are being made. So there are three rules according to Le Chatelier's principle. The first rule is regarding the response to a change in concentration. In general, the rule is if a reactant or product is added to a system, when that system is at equilibrium, the system will shift away from the added component to use the excess up. The converse would be if a reactant or product is removed, the system will shift toward the removed component to make more of it. Let's look at an example of this. The Glencoe chemistry textbook has an online animation which helps us to see changes in concentration, pressure, and temperature, and how they affect the different systems at equilibrium. So let's look at an example of a change in concentration. So we can see in this system there is a orangish colored fluid, and here is the reaction that is going on in this fluid. There is an iron compound, and it is in equilibrium with the iron ion and the rest of this. I think this is thiosulfate. So at equilibrium, we can see there's these certain amounts. So the concentration of iron thiosulfate is slightly higher at 6, let's say this is 6 molar, and the iron ion and the thiocyanate ion are roughly at 4. So what we can do is we can either add a component or remove a component. So let's look first at what happens when we add a component. Sodium thiosulfate is, when it dissociates, it will make more of the thiosulfate ion. So let's add some of that and see what happens. When we add that, we see that immediately that concentration goes up, but we see that it's shifting. We see that in order for the thiosulfate ion to get reduced, meaning we had added more of it, equilibrium is going to seek to reduce what we added, it needs to shift equilibrium towards the left or in reverse, or we would say equilibrium has shifted to favor the reactants, the iron thiosulfate. So the iron thiosulfate is made because in order to reduce the amount of the thiosulfate ion, we're going to bond the thiosulfate with the iron ion, and we're going to shift equilibrium to producing more of the iron thiosulfate. And in response, if the iron thiosulfate is red, we see that the solution has become red in response. Let's go back and look at what happens when we remove something. Le Chatelier's principle says that when you remove a reactant or product, equilibrium will shift toward the removed component to make more of it. So we can predict that if we remove some of the iron ion, equilibrium will shift forward to make more of it. Let's see if our prediction is correct. So if we remove it, we see that immediately it goes down, but now equilibrium is shifting. The system is responding in order to compensate and make more of that iron. So how does it get that iron ion? Well, it has to break up the iron thiosulfate. So we see over time the iron thiosulfate ion went from up here at around 6 or 7 down to 4. And what that did was, when it breaks up, it makes more of the iron ion, so that goes back up, but it in turn also makes more of the thiosulfate ion, so that amount goes up. And we see that because we have removed some of the reactants by turning them into products, and the products are yellow and colorless, we see that the solution has become more yellow in response. Let's look at another example here. If we have a reaction between nitrogen gas, hydrogen gas, and they create ammonia gas and it releases energy. If we have this system at equilibrium, let's look at how we can change the system by causing a disturbance. If we increase the nitrogen in the system will respond by temporarily increasing the rate of the forward reaction until the excess N2 is turned into NH3. This makes sense because we wrote down, according to Chatelier, if we increase the amount of any component, equilibrium will shift in the direction away from that component to use it up. So it makes sense that adding nitrogen atoms as N2, we would want to redistribute those nitrogen atoms, because nitrogen in this system can exist as N2, or it can be part of NH3. And the system wants to have the nitrogen evenly distributed amongst the two different molecules. So if we increase the speed of the forward direction in which nitrogen and hydrogen combine to make NH3, that means the NH3 is going to increase over time. As we're using up the added N2, it's going to decrease, but it's also going to cause H2 to decrease, because H2 is bonded to N2 in order to make NH3. A secondary thing that we'll see happening in this reaction is that for every time NH3 is made, 92 kilojoules are released, because this is an exothermic reaction. So if we are making more of the NH3, we are creating more energy or releasing more energy from the bonds, and therefore the temperature is going to increase. Instead, let's this time look at if we decrease nitrogen gas. Chatelier's principle, again, says that if we decrease a reactant or a product, or we remove it, equilibrium will shift toward the removed component to make more of it. So, if we decrease N2, if we somehow remove that nitrogen gas from the system, equilibrium is going to shift towards the N2. That's the reverse direction. And this makes sense because we have removed nitrogen atoms in the form of N2. We know from the last example that nitrogen atoms want to be equally distributed as N2 and NH3. So in order to make more of the N2 to compensate for what we just removed, we have to break up some of the NH3. In order to break up NH3, we need to use up the energy. So we're going to combine energy with NH3, and when we break it apart, we'll end up with more N2s to compensate for what was removed, more H2s. And then obviously we're going to decrease the NH3 and decrease energy because both of those are being used up. In both of those reactions we just saw, kilojoules was part of the equation that we wrote as a product. So because kilojoules can be written down as a reactant or product depending on whether it's an endothermic reaction or exothermic, we can also use temperature as a component that is added or removed. So the rule number 2, which is the rule for Chatelier's principle regarding changes in temperature, is worded very similarly. In this case, if the temperature is increased, which means that energy has been added, the system will shift away from the energy to use the excess up. So when we add temperature by adding heat or adding heat energy, the system is going to shift in whichever direction goes away from the kilojoules. If the temperature is decreased, meaning energy has been removed, the system will shift toward the energy, whichever side energy is on, reactants or products, to make more of it. Let's look back at our example of the nitrogen, hydrogen, and ammonia. So again, this is an exothermic reaction, meaning that the kilojoules or energy is written as a product. If we add energy or heat the system, so maybe we're going to take this system and we're going to put it in a hot water bath, we will see that the system will respond and it will try to reach equilibrium in temperature again by temporarily increasing the rate of the reverse reaction, because the reverse reaction is the reaction that goes away from the energy. So when we go away from energy, what we're saying is that we're using the 92 kilojoules to break the NH3 apart and turn it back into N2 and H2. So what we'll see over time if we're trying to use up this energy is the extra energy will be used up, so it'll go back to being at equilibrium. However, the amount of NH3 is going to decrease because we are using it up, and the amount of H2 and N2 will increase because they're being created. If we did the opposite and we removed energy or cooled the system by, say, putting it in an ice bath, equilibrium, as we have learned, is going to shift toward the removed component, which in this case is the kilojoules. It's going to shift towards the component to make more of it. So if we're making more energy, in order to make energy, we need to make NH3. So we're going to use up N2, we're going to use up H2 by bonding them together, and we're going to make NH3. We're also going to be making energy, and as we release energy, it's going to warm the system back up so it will go back to being at equilibrium. Now we need to look at the third part of Le Chatelier's principle regarding pressure. When we're regarding a change in pressure, it's a little bit different because pressure is not written as a component in the reaction equation. So we have to think a little bit about the gas laws we learned about back in Unit 13. So if the pressure, the rule says, on a system is increased, the system will shift toward the side with fewer gas molecules, meaning it will shift towards the reactant side or the product side that has fewer moles written into the equation. If there are fewer molecules in a system, then that means there's going to be fewer collisions with the walls, and that means it's going to be decrease in pressure, so we're relieving the change in pressure. So again, equilibrium always wants to shift to reduce whatever change has been imposed. So if we are increasing the pressure, the system wants to shift to reduce the pressure. The opposite case would be is if we decrease the pressure, equilibrium wants to seek to replace or compensate for the pressure that's been removed. So equilibrium will shift toward the side with more gas molecules to compensate for that lack of pressure. So when we are looking at an equation for a reaction, we have to look at how many moles there are. And this is a little bit different than we're used to thinking of with the gas laws, because in the gas laws we used the combined gas law, ideal gas law, Boyle's law. Those were all regarding ideal gases, and part of the definition of an ideal gas is that it is a gas in which the components are not reacting or attracting to each other. This is different when we're talking about a chemical reaction. So we can't rely completely on those rules, but we can say that without a doubt, the fewer molecules there are in a container, the less the pressure will be. So let's look at this in a demonstration with that animation we looked at previously. Here we have a system of gases, one of which is purple, one of which is colorless. So we can see when we change the pressure on this system how equilibrium is going to shift, because we can see that there will be a change of color. They have also provided an animation of the two different molecules, and we can also look at their relative concentrations. So here's the reaction for this system. It's iodine gas, meaning it's a diatomic molecule, two iodine atoms bonded together, which are represented as two purples bonded together, because I2 is actually a purple color. If those unbond and we have two separate iodine atoms, it becomes colorless, and it is just represented as an iodine atom. Now we know, because of the notes we just took, that when we're looking at moles or looking at pressure, we have to look at the number of moles. So if we increase the pressure by, let's say, we're going to move the volume so that the volume is smaller, we're going to see that the system is going to shift. Right now, here's our balance between the amount of iodine molecule and iodine atom, and it's going to shift towards the side which takes up less energy. According to the moles, there's two on the right and one on the left, so equilibrium will shift towards the left, because when you bond two atoms together, they take up less room. And this is also a purple color, so we see that the solution has become more purple. So we changed the volume, which means we changed the pressure, but the system compensated by shifting to the side with fewer moles. If we reset the system and we decrease the pressure, we would see what we would expect, and that's that it's going to become more colorless because we're going to be shifting in the opposite direction.